Welcome to another episode of the Agronomy Highlights podcast. I'm your host, Ryan Spellman, and I'm joined here with my lovely co-host, Dwayne Miller. Dwayne, how are you doing today?
Doing great, Ryan. How are you?
I'm living the dream, Dwayne, and it's great. We have two episodes in a row that are just me and you. So, we love Justin, but we're having a fun time over here,
We're
right?
giving him some much needed time off for some resting and relaxation, rebuilding. He might be stuck in a winter meeting somewhere at this point, right?
That's right. It's been a long season of winter meetings, but spring is on the horizon. And actually this episode was one of Justin's brainchilds here. The theme this year has been getting a little bit back to basics of understanding the inputs that we're putting in so that we can reduce the cost of the inputs and really understanding some of these basics to do a better job in some of our economic contexts. And I think that's really important when it comes to phosphorus, right? So today, that's exactly what we're going to talk about. We're going to talk about dynamics of phosphorus in the soil, some of the new technologies that are available for managing phosphorus, and some of the best management practices.
I think you're right. We're gonna talk about some basic stuff. We're gonna cover those building blocks of what phosphorus does and how it moves, but then we're going to get into some of this really cool new technology that's being developed to help make us more efficient in what we're doing. And it's going to boil down to economics, right? We're coming into some tougher times again. We got input prices going up. There's a lot of geopolitical things happening lately. I think this is a really hot topic. So I'm anxious to dive into it.
Yeah, certainly. Yeah, let's just jump into it. So you mentioned, we're going to be talking about these new technologies that are coming. And so we have someone from industry joining us today. That's going to be Steve Levitsky from Phospholutions. And he's going to kind of share about what they're doing when it comes to some of their rhizozorb products that are increasing phosphorus efficiency. And then we have a friend of the show. He's been on multiple times. That's Dr.
He's a rock star with us, right?
Yeah, he's been on a lot. Anytime we have a nutrient management question, he's our go-to, and he's taking time out of his sabbatical to talk with us today. And that's Dr. Charlie. So he's our nutrient management specialist, and he's going to kind of fill us in on a lot of the agronomic context of phosphorus management and how he sees some of these products in the broader perspective of phosphorus management. So yeah, I'm excited for it. And before we introduce our guests, here's a word from our sponsors.
Most people think fires start with flames, but they don't. Most flames start with heat. Control the heat, control the outcome. That's why Mark Twinoffel with Midwest Ag Risk Control focuses on one question. How fast can you control the heat? Around the farm or in the field, Mark recommends the Enforcer One system with Firebowl foam, built to cool fast, cling to surfaces, and stop reignition. To find out more about this system, call or text Mark at 618-521-6805 or online at enforcer.com.
Are you or your ag-related business interested in becoming a sponsor of the show? Support Penn State Extension's mission to provide trusted, research-based agronomy insights by sponsoring Season 4 of the Agronomy Highlights podcast. Advertising opportunities are available, and you can register directly or take a look at the sponsorship packages and pricing in the link below in the show notes. Feel free to reach out to me directly by emailing rms6953@psu.edu if you have further questions. Now, back to the episode. So with that, let's jump right into it. Charlie and Steve, why don't you go ahead and introduce yourselves and kind of what you guys do surrounding nutrient management and phosphorus.
Hey everyone, good to see you today. So I'm Charlie White, Soil Fertility and Nutrient Management Extension Specialist on the agronomy team and member of the Plant Science Department here at Penn State. And our group, our extension program really focuses broadly on nutrients and other soil amendments to help drive crop yields, but also looking at it from cost perspective, trying to enhance and maintain profitability for farmers, and also an environmental perspective, try and reduce nutrient losses into the environment so that we're all good stewards of the planet that we live on.
Yeah, thanks, Charlie. And I should have said reintroduce Charlie because he's been on here plenty of times. So he's a friend of the show at this point. Okay, so yeah, now Steve, why don't you introduce yourself?
Hello, everyone. Steve Levitsky. I'm the Chief Administrative and Sustainability Officer here at Phospholutions. I've been here for 5 years, March 1st. So hard to believe it's been that long. I was number 7 in the corporation, and we've built it up to 25 people. Previous to that, I was the VP of Sustainability for Purdue Farms, reported directly to Jim Purdue and the CEO there. And then prior to that, I was the Director of Global Sustainability at American Sugar Refining. So I've got a long experience in environmental soil science and agronomy and how it translates into food and manufacturing food.
Steve, thanks for joining us. Can you just tell us real quick about Phospholutions and what you guys do there first?
Sure. So we're a startup spun out of Penn State Technology. So my boss, CEO and founder, Hunter Swisher, was actually an undergrad at Penn State. Had a class with Jonathan Lynch, who's a plant science professor, who talked about this technology he had developed, an IP he had developed. Hunter raised his hand, said, "What are you doing with it?" And at that point in time, Dr. Lynch was not doing much with it. And Hunter licensed 2 of the patents and started Phospholutions in 2016. So from there, what I will say is we've now developed 11 additional patents and really have taken the technology that was developed at Penn State and kind of put it on steroids. And I think Charlie could talk to that, of seeing the progression of our formulations and our product over the last 10 years is really pretty amazing. But the main thing with our technology is it absorbs and desorbs phosphorus in a very unique way, which allows it to feed the plant as P is needed. So essentially, the P doesn't get locked up in the soil, and keeps the phosphorus readily available to the plant. And from that standpoint, our value prop to the farmer is: look, you're going to save about 10% per acre with our product. You could apply 50% less P2O5 and get the same yield. And we've proven that out over and over again across the Midwest and here in Pennsylvania, that the farmer can get the same yield and place 50% less P2O5. So great option. And then from an environmental standpoint, it's about a 78% reduction in P runoff, which is some research we did in New Zealand. Charlie's done some work with poultry litter with just our active ingredient, showed a 50% reduction of runoff from those studies. And then from a carbon perspective, we've done a life cycle assessment. It shows mine to farm yield about a 45% reduction in carbon emissions in comparison to a MAP product, monoammonium phosphate, and actually a much larger reduction if you switch out DAP put our product in place of DAP.
Got it. Thanks, Steve. Yeah, I think it's the Penn State element of Phospholutions is a cool example of how like extension and Penn State works in a cooperative setting, right? That we work with the farmer and industry, and I think it's kind of a cool thing to highlight. So let's jump in and let's start this conversation with phosphorus, right? So like we're talking about phosphorus today. Let's get back to kind of the basics of it before we expand this conversation on, how we can be more efficient with it and why that matters. And then, talk about some of these new technologies further. So I'll just pitch this, why is phosphorus important to crops in general, right? Like today, maybe we'll think about our field crops, and what does it do and why is it so important, critical for growth in plants?
Sure. Well, if you look at the role of phosphorus in the plant, it does a couple of things. First of all, it's part of the backbone of DNA, right? And so we hear a lot about DNA, whether that's, at a crime scene or whether that's gene editing of crops or things like that. But, all organisms need DNA and they need to replicate their DNA, and phosphorus is the backbone of that. So think about where a plant would be without the ability to reproduce DNA in every cell. The other thing that it's really critical for is it's the sort of the energy currency. So there's a molecule in plants called ATP, which is adenosine triphosphate. And that's what the plant uses to generate energy and move energy around between cells. Where would a plant be without that ability to transfer energy, from, say, leaves into the grain or, other parts of the metabolism. And the last thing I'll say about it is that most of the phosphorus at the end of the plant's life cycle ends up in the seed and in the grain. And that's because phosphorus is critically important for flowering and seed set and grain development. So, you look at all of those things and think about the importance of all of those fundamental sort of biochemical things to produce DNA, to be able to move around energy, to be able to set grain, right? You can see why it's one of the three essential macronutrients that we talk about with plants.
Yeah, great. I think that's a great foundation, right? Like we need seed in most of our crops. We need DNA, we need energy. So you hit all of like the really important functions of our crops, are very reliant on phosphorus. Now, how are we commonly, I think when we think about phosphorus, it's going to be very different how you manage phosphorus based on your system, right? Like some folks are using a chemical source of phosphorus, some are using an manure source, and each one has their own challenges. And I know there's people who are managing for removal of phosphorus. So, that's a lot of questions in one. But can you talk maybe about how in Pennsylvania we generally think about fertilizing for phosphorus and what are the different ways to do that effectively?
Sure. Well, as you mentioned, we can immediately divide strategies into two different camps. One is manure, and the other would be fertilizers. And I'll start with manure. And manure is a great source of phosphorus. In fact, it's too good of a source of phosphorus because the ratio of nutrients in manure is not balanced to what plant needs are. If you are applying manure at a nitrogen-based rate, you're often applying maybe 2 to 4 times as much phosphorus as the plant actually needs. Just happens to be what the ratio of availability is in manures. And so that can be a challenge with a lot of soils in our state, especially in the southeastern part of the state where we have a lot of the livestock industry is centered around there, and manure accumulates in that region. It's kind of expensive to transport manure long distances. Easier to do with, say, poultry manure that's dry, but pretty difficult with dairy and swine manure. So in those types of systems, actually, phosphorus is built up way beyond what the crop needs, and in many cases, it's built up to an environmental concern where we have issues of runoff, whether that's soluble runoff leaving the surface or whether that's with soil erosion. Those are the two main pathways of loss. Now, if you look at the other side of things, it's the fertilizer management. And actually, one time I put together a map of Pennsylvania and looked at the soil test levels and what they were relative to the agronomic optimum. And once you get into the western half of the state, the median soil test levels of our fields are actually slightly below optimum. Very different story than in the southeast, where they're mostly above optimum. So you can kind of see that play out just in the spatial difference of where the manure is. And so western part of the state, we're definitely managing mostly with fertilizers. There's 3 main types of fertilizer, I would say. There's monoammonium phosphate, which is MAP. There's diammonium phosphate, which is DAP. And then we have a liquid phosphorus, 34O, polyammonium phosphate, or poly-N, some people call it. So those would be the 3 main sources. And then I see the liquid phosphorus really being placed as a starter fertilizer, where farmers might use 3 or 4 gallons, put on with the planter. And that's just to help get the crop started, and that placement is really important to be right near that germinating seed so the roots have easy access to it. But that liquid phosphorus is about twice as expensive as the granular phosphorus. And so most farmers don't meet all of their phosphorus requirements with that liquid. They're going to use some MAP or DAP broadcast over the field. And if they're in a tillage system, maybe that's tilled in. If it's no-till system, it's just left on the soil surface. So those are the most common ways to fertilize with phosphorus.
So when we talk about managing our bank in the soil, if you will, phosphorus is different than our other 2 macros in nitrogen and potassium. And can you guys talk a little bit about how we would manage that phosphorus bank?
Sure. So one of the unique things about phosphorus is that it's very tightly held to the soil. And when we add it as a fertilizer, it's usually in a highly soluble form. The chemical form is PO4 3-. So a phosphorus atom with 4 oxygen atoms and 3 negative charges. And those oxygen atoms with the negative charges really like to bind tightly to things like iron and aluminum. If our soils are slightly acidic, usually we're going to have iron and aluminum phosphates that precipitate and become unavailable. If our soils are alkaline, it's going to bind up with calcium phosphates. The longer the phosphorus fertilizer that's initially very soluble, the longer it sits there in the soil, the more and more it reacts with iron and aluminum and calcium to become unavailable. And once it becomes unavailable, it's like locked up and is going to just very slowly trickle back out. So, in terms of building up your soil phosphorus levels, historically, what we've said is 30 parts per million on a Melic 3 extract is the agronomic optimum. And what that really means from what's happening in the soil chemistry is you've built up your pool of insoluble phosphorus enough that the trickle which is coming out is going to meet the crop need, right? And it actually takes a lot of phosphorus to build that. It takes a lot of phosphorus inputs to build that bank up enough such that your trickle coming out is enough to meet the crop supply. So that's a real challenge with phosphorus, is the need to really build that bank up over time so that it can overcome that binding. Steve, I know the Rhizosorb technology with Phospholutions is designed to overcome that problem. So do you want to say anything about how your technology works in that regard?
Yeah, definitely. And first, I wanted to actually mention, and I think this is correct. You can correct me if I'm wrong, Charlie. I believe so. I'm showing my age here. So I studied soils way back in the 90s, and I know at the time that the philosophy was you could bank as much P as you want, and that was what was told to farmers. And that's kind of where we've gotten to today, where now you have animal ag areas where I have really high P because they were told, hey, yeah, bank that ends the problem, right? And I believe Dr. Sharpley was the one that kind of stepped back and said, wait a minute, that stuff will come off the farm with sediment and started the P index. So giving a call out to Penn State and kind of, one of the front runners there. But yes, on our technology side, so Rhizosorb is, as I mentioned before, is a product that will both absorb and desorb phosphorus readily. And so essentially we have weakly bound phosphorus. So as Charlie mentioned, you have aluminum and iron in the soils that will capture P. And I think the most of the peer reviewed articles show about 20% of the P that you place in that growing season will make it to the plant. And then if you look at how much P makes it from what you put on the crop to what gets to the fork, it's 10% of that phosphorus. So very inefficient system. So what our product does, and as I mentioned before, also is we suggest to farmers to reduce up to 50% of the P2O5 you could put down and get the same yield with our product versus a MAP or DAP. The reason that is our product is able to hold that P in a readily available state, and then when the plant needs the P, is the P2O5, the phosphorus content goes down in the soil water complex, our product will liberate that P and feed the plant. And actually, another thing that we've figured out over the years of research we've done, MAP and DAP will get locked up in the soil in that first month or two of the growing season, and then you'll have deficient P across the growing season, where our product will continue to feed the plant throughout the growing season. So from that standpoint, we kind of take away that restrictive soil P that farmers are relying on throughout the growing season.
Yeah, and so this is an interesting conversation, right? Because we talk a lot about how P behaves in the soil, and when we think about, something that we have to dose to the plant at a specific time, we often think about nitrogen, right? But it's a very different loss pathway that we have with phosphorus, right? We're not losing it because it's so mobile, right? We're losing it because it's so immobile, right? It's getting bound to the soil. So I'm curious, just to go back a little bit, and Charlie was mentioning that it sounds to me there's two ways to think about this, right? Either we need to fill up all that soil space, the capacity of that soil to hold P, so the trickle is enough to allow for crop, uptake, or we need to dose it at very specific times throughout the season so that we get it in its mobile form to the plant at the right time. So that's kind of what, or, then on Steve's end, or we have this product that helps to bind the phosphorus away from the soil and make it more accessible, right? So those sound like three very distinct strategies that you might use in distinct contexts. But when I think about that first strategy, Charlie, that you mentioned, where we're building up the soil, saturation of phosphorus, Are there environmental hazards that come with that, right? Because a lot of times we talk about having too much phosphorus can lead to runoff of phosphorus, and that becomes a problem. So, how does the environmental piece fit into this?
Yeah, that's a great question. I'm glad you brought that up. So, when I talked about the agronomic optimum level being 30 parts per million, that's actually a level where if you're maintaining around that level or even just a little bit above, let's say you're in the middle of our optimum range, which is, 30 to 50. So, let's say you're at 40 parts per million. That's actually pretty low in regard to what would become a risk for environmental losses. So we start to think about environmental losses becoming a concern when you get to, say, 200 parts per million. And someone who's managing their fertilizer program carefully and making economic, rational decisions probably isn't going to get to 200 parts per million with fertilizer. But in manure-based systems, it's very easy to get there because of that imbalance of the nutrient levels in the manure and the high phosphorus content of manures. Now, that said, you could still have a soil with, say, only 30 to 40 parts per million phosphorus, and depending on how you manage and apply that phosphorus, you could still have losses. And the big issue with this is putting fertilizer on the soil surface at times of year, and this could happen with manure too, fertilizer or manure, really any phosphorus source, putting that on the soil surface and leaving that exposed to runoff during times of year when we have runoff, right? So this would be, here we are in early March, perfect time of year for runoff losses to occur. So, and that's a big challenge with no-till production because we usually aren't tilling our fertilizers into the soil with no-till. Now, no-till is great because it reduces our erosion losses, and we can lose a lot of phosphorus with erosion, but it's not a complete cure to the environmental phosphorus problem just to go no-till, because if you're leaving your fertilizers on the soil surface, you're sort of trading one problem for another. So I do think it is important to think about the placement of phosphorus fertilizers or manures and try and get them somehow off of the soil surface, incorporate into the soil somehow. And that might not be with full width tillage. Maybe that's putting it on with a planter and getting it, buried below the seed a little bit or a little bit to the side of the seed. With manures, maybe that's using some type of low disturbance injection technology, or maybe it's using reduced rates. Like one of the real benefits of the Rhizosorb I see is that you're putting out 50% less phosphorus, and it's in a form that isn't necessarily immediately soluble in terms of like going into soil solution. It's sort of bound up with that active ingredient. So 50% less material on the soil surface, bound a little bit more tightly in a weak type of binding with the active ingredient. And, they've got results of runoff studies that show 78% reduction with their technology. I'm not sure if that includes the 50% reduced application rate, Steve, or is that just 78% reduction with the same PT?
That's the 50%. So the study was done at 100%, 100% MAP, 100% our product. And then if you do it at 50%, that's where the 78% reduction of water extractable P happened.
So oftentimes in nutrient management, we talk about those 4 R's, and Charlie, I think you hit them all there. We're talking about the right source of material there. You're looking at the correct rate, using it at a proper rate, right, and looking at timing. And you mentioned possibly dosing this material out there to create better nutrient stewardship and correct placement. So I think we checked off all 4 of those boxes for our 4 R's.
Yeah, and one thing I'll go back to too, Ryan talked about sort of these 3 different strategies, and I would say traditionally farmers have used at least 2 of the strategies where they put a little bit on as starter and they place that very intentionally next to the seed. And that's sort of what you might call like the micro dosing. But then they put the balance of their requirement on as a broadcast and sort of use that to build up the bank to keep that trickle going strong enough. So I think farmers typically have used both of those strategies in combination to a reasonable effect. But I think there's opportunities to continue to use technologies, whether it's Rhizosorb or other technologies, to adjust how we do that and continue to fine tune our management.
Yeah, I'd say that the kind of the rate side of the 4 R's is where we come in. Obviously, is your our thinking with it is the rates that are applied today are applied to put into the bank and hope it gets to the soil or to the plant. And so you're over applying phosphorus to load the bank. Now, as I mentioned before, if you've got only 10% getting to the plate or 20% getting to the plant, that sounds like a pretty bad return if you're for the dollar. So you're putting $1 of phosphorus down and only 20 cents is getting into the plant. That most farmers would probably, if you really thought about it that way, would be like, well, wait a minute, this is the wrong way to feed a plant, right? And so that's where our product doubling the potential for that pea to get to the plant increases the efficiency and gets the product to the plant when it's needed.
Yeah, so this is probably a place to talk about the economics of phosphorus, right? So Steve kind of mentioned that when it comes to at least what they're working on, it's reducing that rate so that you can save some money. And kind of across a lot of our shows this year, one of the big themes has been, okay, how do we farm with less money, right? But I think the price of a lot of inputs is going up. And economically, it's really hard to do what we do. So that's kind of been a theme of why we're covering some of these topics, to learn a little bit more of how we can be smarter about the way we use things. So Steve, maybe you can talk a little bit, because in kind of the green room ahead of time, you were talking to us about the economics surrounding phosphorus. Where are we when it comes to the current state of economics of phosphorus? Is it getting more expensive for farmers to use? How do some of these geopolitic things influence our ability to bring in phosphorus? Where do you see this going? And why is it important that we think about the rate we're using and purchasing?
Yeah, so phosphorus fertilizer is really expensive right now in comparison to years past. I'm just looking at some information just this week. Looks like MAP is around $700 a ton, and so yeah, you've got a high price for a phosphorus fertilizer today, and farmers are also dealing with low commodity prices where the corn and soy aren't getting the dollar they need, and so then it's they step back and say, okay, well, if this input is this expensive, do I add phosphorus this year or not? And then take the risk of, okay, well, if I don't add phosphorus, does my yield go down substantially? So, and now with the crisis in the Middle East, a large portion of phosphorus fertilizer comes from that region, and so there is potential for this to go up even further, especially in the monoammonium and a diammonium. The ammonia does come from Iran and other locations, and so essentially you're going to probably have a spike in costs. So from that aspect, farmers are looking for how to reduce the use of phosphate fertilizers or find other avenues to get the pea they need, which again is helpful for our product because we are about 10% cheaper per acre for a farmer. And also there's less product going out. So essentially it's less passes and less weight on the tractor. So essentially you've got some cost savings there that we typically don't even include in our reduction. But yeah, it's a global issue. And the other part of it that most people don't think about. So the Trump administration had just put through probably about a month and a half ago that phosphorus is now considered a critical mineral by the USGS. And an executive order just came through on the protection of phosphate. And so the concern is currently most phosphate comes from a handful of countries. And the phosphate mines in the United States have a life of about 30 to 50 years left of economically viable phosphate that they could pull from that rock. But 75% of the phosphate across the globe is located in one country, located in Morocco. And so the reason for the push on the critical mineral side is like, okay, if we've got 30 to 50 years left, how do we extend the life of that mineral? Because once that goes away, we're going to be looking at purchasing it from some other countries, and then it's a geopolitical risk and a risk to growing our food here in the United States.
That's interesting. It's interesting to me that it seems like and I think this is with a lot of our different nutrients. Like for a nutrient that's so important, like how actually tricky it is to get and how limited it is. And I think this is going to, impact. It seems to me will impact our folks that are focus on crop production and don't have livestock integrated into the field, right? Because on the other hand, if you have livestock, manure is a good source, right? So that, at least that's kind of how I'm seeing it. So, Dwayne, any other questions that you have for them on kind of the management side before we get into some of the new technologies?
No, I just, as I put my farmer hat on here for a minute, and Charlie, I keep going back to that presentation you did a couple years ago and coming up with a plan when fertilizer prices are high and commodity prices aren't so great. And it just seems like that might, it's kind of a reoccurring theme here. How do farmers, are they going to adjust their fertilizer input strategies when we get into a situation like this or not this coming year? So all things I think to think about as a production person.
Yeah. Well, I'll say a few things about that because, anytime we have some of these shocks to the economic system and fertilizers are just so vulnerable to so many things. One of the things is they're very energy intensive to manufacture. So anything that affects global energy supply is going to, ripple through the fertilizer markets. They're heavily traded global commodities. And a lot of times we're not trading with our best friends, right? We're trading with some of our adversaries. And so anytime, we start to have sort of political issues with some of the other power players in the world, it ripples into the fertilizer market. So it's such a vulnerable commodity to these things. And it's one of the most expensive inputs for farmers. I think it's about a third of their input costs are just tied up in fertilizers. So a couple things for farmers to think about. Our fertilizer recommendation strategy is called the build and maintain philosophy. And the idea behind that build and maintain is that you build up to the optimum level. And once you've hit that optimum level, theoretically, you've got enough nutrients banked in your soil to grow a crop that year without any additional fertilizers added. And that's one of the great things about the build philosophy, right? So some other universities, maybe some of the Midwest universities, they're more on like a spoon feed the soil and sort of maintain suboptimal fertility levels. And every year to year, you look at the economics and how do I fertilize and whatnot. And it's a lot more challenging for farmers that are sort of chronically maintaining suboptimal nutrient levels and relying on those annual inputs. So it's sort of like, keeping a full tank of gas in your car, right? You see a hurricane on the horizon, first thing people do is they go up and they fill up their gas tank, right? So soil nutrients are kind of the same way. I would say when prices are low, it's worthwhile investing in building up the nutrient levels, at least for those nutrients that can be stored in the soil, like phosphorus and potassium and calcium and magnesium. Nitrogen, obviously, that you manage that on an annual input because anything you put in this year is probably not going to last till next year. So I think that's something. And if you're a farmer here and you're looking at your soil test levels and you're in that optimum zone already and you're thinking, should I pay to maintain myself in this optimum zone this year when fertilizer prices are so high? I might take a year off on purchasing your inputs if you're comfortably in that optimum zone, or if you're in the above optimum zone for sure. This is a good year to take a year off from purchasing those inputs, ride a little bit on your reserves and wait for the markets to cool off a little bit on the fertilizer prices. The other thing I think about too is how this affects the value of nutrients in manure. I'm going to put a little plug into an online calculator that we have on our extension website called the Manure Nutrient Value Calculator, and we can put a link to that in the show notes. The things that calculator does is it helps you understand what's the nutrient value in your manures relative to fertilizer. So part of the inputs in that tool is what's the cost per ton of MAP or DAP, what's the cost per ton of potash, what's the cost per ton of urea or UAN. And then it takes that cost per ton and it converts it into your manure nutrients and shows you, per 1,000 gallons or per ton of manure, what the economic value is. And the last thing it brings in is what are your existing soil test levels and your fertilizer recommendations. And if your nutrients are in the above optimum zone on a soil test, you're really not getting any economic value out of that manure. And so I think about the value of manure on one farm that has above optimum phosphorus levels. The value of that manure is going to be a lot less on that farm than it will be for a farm that has below optimum phosphorus levels. And so that calculator could help you think about, hey, is this an opportunity where I could sell some of my excess manure, truck, if it's poultry litter for sure, could I truck that out into Western Pennsylvania and get a little bit more for it this year than I might have been able to in the past because of the high fertilizer prices? So I think that's a neat tool for farmers to kind of look at their options and maybe weigh the cost of purchasing some manure versus purchasing fertilizer, or maybe putting a little bit of extra effort into exporting some of that manure and converting that back into dollars for the farm.
Yeah, I'll put my Purdue Farms hat on and chime in. But yeah, that's I remember when I was working for Purdue, there was a legislation coming through in Maryland where they were going to restrict pea application in Maryland, and there was going to be about 200,000 acres of farmland in Maryland that was going to be restricted with application of poultry litter and phosphorus. And so the big concern on the lower shore was, oh, where are we going to put all this poultry litter that is, basically made every year from the production ag, and the concern was that are you going to have a bunch of extra manure left? And what they found was actually the price of poultry litter went up. So it was I think at the time it was about $20 a ton if you sold it off farm. And when that regulation went through, it actually went up to $35 per acre, and they were shipping it up to parts of Pennsylvania, Western Maryland. And it was exactly what Charlie was talking about, where people were looking at it and say, like, look, if I buy this, nitrogen and phosphorus in a chemical form, I could actually get, this other material that's poultry litter and apply it. So yeah, I think it is something the farmer can use as, especially in the high input price timeline, as an alternative. I think the big thing, as Charlie said also, is, when you start talking about dairy manure or other manures where you're moving water around, it just doesn't pencil from a financial aspect. But with poultry litter, it made sense.
I like the fact that, Charlie, you mentioned soil testing a couple times back there in your last comments. And so I think sometimes we neglect to even think about some of the basic things. And as we're thinking about our nutrients, phosphorus can often be said, oh, we've had a history of manure. I think we're good here. We might not think about it in the broader context, but encouraging folks to absolutely at the basic level, just make sure you're doing your soil tests so you know what those testing levels are, and you can appropriately build that bank if you need to.
Yeah, so I think this is I think we had a great discussion here about some of the context around using manure, using chemical fertilizers of phosphorus, sources of phosphorus, and just how we can think about this as a farmer, and how the opportunities that we can save money or spend money to manage this effectively. I think we did a great job of discussing that, and I hope that's helpful for our audience. Now I kind of want to move into the discussion about phosphorus technology. So I think to answer some of these questions, we are seeing a lot more products out there, Phospholutions, and offering some of those products, and then some other products out there that are intended to increase the efficiency of phosphorus. So I wanted to discuss some of those and understand them a little bit deeper. So Steve's kind of already introduced their product, and it sounds to me that this falls into the category of enhanced efficiency or controlled release. I think that's one term. And then some other terms that I've heard are phosphorus biologicals, phosphorus promoting biologicals, or phosphorus solubilizing microorganisms. So that's a lot, but could you guys decipher, what some of these terms are, and what the different categories of some of these enhanced efficiency products are?
I could talk to our product. I don't want to,
Sure.
I'm not sure if I could talk to the others as well as Charlie could, but from our side, we are today considered an enhanced efficiency fertilizer in the state of Pennsylvania. We're currently going through the APCO approval process. We're tentatively approved by APCO, which is awesome. And so essentially it's just us increasing the phosphorus use efficiency to the plant. So essentially our product, as I mentioned before, will propose a 50% reduction of P2O5, get the same yield, and we've proven that out across, actually at this point, 14 different countries we've done research in. I think we're at 18 or 20 states across the U.S. And so it's not a kind of one-time couple small plot studies here. We've done this across large farm trials across the United States and proving it out. So yeah, so from the EEF standpoint, in Pennsylvania, farmers can actually go for CSP or EQIP cost share dollars. And last year when I talked to USNRCS, essentially the if they applied and got the funding, it would fully cover the cost of our product to put our product down versus putting a MAP or a DAP product down. So from our side, we deal more on the chemistry side of things. We're not a biological, but yeah, we do a great job in increasing the efficiency of delivery of phosphorus. And Charlie, I don't know much about the biologicals and other things, so you might want to fill in there. So
Yeah, I can talk a little bit about some of the biological processes, and I'll say I haven't had a chance to experiment with any of the other phosphorus technologies besides Rhizosorb, so I can't really say, well, there's a great product that's going to do this or that, but I'll try and explain a little bit of the background, and then I will also say I'm maybe a little bit skeptical about the possibility or potential of some of these biologicals, but I also will readily admit I've not tested them, so I can't say, well, I've got conclusive data that they don't work, but I'll explain a little bit about where I think some of my skepticism comes with. So, we talked about the tendency for phosphate to get bound up with iron and aluminum or with calcium. And so one of the ways that you can kind of reverse or protect that binding up is through organic acids. And the organic acids, what they'll really do is they'll actually hold on to the iron and aluminum, or they'll hold on to the calcium and prevent them from binding up with the phosphate. So you sort of free up that phosphate by holding captive the iron and aluminums and calciums on these organic acids. The other thing that maybe some of these microbials are doing is exuding the phosphatase enzyme into the soil. And what phosphatase does is it really breaks apart organic phosphorus molecules. And a lot of our phosphorus in the soil is in the organic matter pool, right? Whether that's from manures or whether that's crop residues, right? I mentioned the DNA and things like that. There's also like phytic acids and phytate and things like that. Those are all organic forms of phosphorus. And the phosphatase enzyme will help break those molecules up and release the phosphate in a plant available form. So I think some of the biologicals out there are either basically trying to promote organic acids or they're trying to promote the phosphatase enzyme. Now, the reason I'm a little bit skeptical about the potential of these products is because every teaspoon of soil contains 1 billion microbes in it already, right? And we've also got plant roots there that are exuding organic acids. And so really the building a healthy microbial community, maintaining a healthy root system in the soil, those are all things that I think are going to go the furthest in terms of promoting this biological cycling and enhancing biological availability of the nutrients. And so then, adding some new microbe to that community, to me, it's unclear to me how much that additional dose of that microbe actually impacts things beyond what the soil is already doing. And then I'll bring up one more kind of biological that I didn't mention yet, and that's the mycorrhizal fungi. And these are one of my favorite organisms. Actually, my master's degree at the University of Maryland was all on mycorrhizal fungi. Ryan, I know you're a big advocate for them too. Was that part of your research on mycorrhizae as well?
Yep. Part of my thesis work was on mycorrhizae. Yep.
Okay, awesome, great. Another mycorrhizal scientist here. So, mycorrhizae are essentially they're beneficial soil fungi, and they form cooperative relationship with the plant root where they're exchanging energy. The plant root is providing energy to the fungus, and then the fungus is bringing nutrients back to the plant, and especially phosphorus. And so phosphorus is so immobile in the soil that these mycorrhizal fungi, they go out and they extend the plant root system, and they help that plant root explore a much greater volume of soil. And the mycorrhizae can pick up that phosphorus, and then they bring it back through their mycelium to the plant root. And some of my research at the University of Maryland showed that soils that had been in no-till agriculture and had high levels of mycorrhizal colonization early in the growth of the corn root, the plants were taking up 2 to 3 times as much phosphorus because of that mycorrhizal colonization. There was a very strong relationship between mycorrhizal colonization and phosphorus uptake by the plant. And so there are some things that we can do to really promote mycorrhizal fungi. And it's not about inoculating your soil with a mycorrhizal product, because these fungi are there in the soil already in large numbers. What we need to do is we need to cultivate conditions that are good for their growth and development and maintenance. And some key things to do is to reduce soil disturbance. So every time you till the soil, you're basically breaking up all their biomass, and they have to spend a lot of energy repairing their whole network, right? And then where do they get that energy from? They get it from a plant root. So if you till the soil and then don't have a plant root there, like have a cover crop planted or a cash crop planted immediately, right? You're basically starving that fungus and it can't regrow. And so then its population slowly die and die and die. So reduce soil disturbance through no-till, keeping the soil covered with plants year-round through cover cropping. Those are key things that you can do that aren't about buying, some bugs in a jug. It's about good, solid, sound agronomic soil management. It's really going to bring those mycorrhizae to life and help a lot with phosphorus acquisition.
Yeah, I'd be remiss. So I want to share one quick thing about mycorrhizae that I found absolutely astonishing when it comes to phosphorus. When I was doing my work in grad school, we were looking at how mycorrhizae triggers defenses in plants. And so anyways, part of this is we took corn that did not have the gene that allowed it to associate with mycorrhizae. It didn't have that gene in it, and we planted it in the field next to the same corn that had that gene intact. And what we found is the one that had the gene intact, so it could associate with mycorrhizae, it grew like normal corn, and you had ears, and we didn't see much of a nitrogen deficiency. It was a droughty year, so there was a little bit of drought stress. And then the corn that couldn't associate with mycorrhizae in the soil, it grew about half the height of that other corn, and everything was purple. So clear signs of, leaf tips being purple, a sign of phosphorus deficiency. And so I think because of, the mycorrhizae helps with drought tolerance and phosphorus uptake, and both of those, the corn didn't even produce an ear. It stayed half this height and didn't produce an ear just because it didn't associate with mycorrhizae. So I thought that was interesting, and I think it's to your point, managing the soil environment is really important to promoting that. So now I'm curious. So I want to hear from both Steve and Charlie on this one. When it comes to phosphorus technology moving forward, where do you see the future is with some of these products? From Steve's perspective, what are you guys moving towards? What are some of the things you want to see happen in the future? From Charlie's, what are you seeing when it comes to research and looking at some of these technologies in the future?
With this conversation today, my brain's been running. Actually, I was thinking about calling Charlie after this show and talking about a couple of things we might want to put in the field next year. But from our Phospholutions standpoint, we've got our 839 fertilizer product, and that product, the way it's made is the active ingredients injected right into the phosphorus production process, and so the phosphorus is absorbed to our active ingredient, and then of course it acts like a sponge and it adsorbs. The thing we don't have out today is a commercialized just active ingredient product. So we're doing research on that and how we can do that, and that's more on the financial side. How do we do it so we make it a best thing for the farmer from a price side of things, and what's the WIFM for the farmer that they get out of it? Charlie's done a lot of research on our product and showed what it does from an environmental perspective. We didn't talk about how we actually did some work with Charlie where he just put our active ingredient in with an optimum soil and met the same yield as a MAP product. So that's the type of stuff that we really want to try to look at. And to Charlie's discussion earlier where he said, look, if it's a high price phosphorus year, maybe you don't apply phosphorus. Well, how do you apply a Rhizosorb active ingredient to your soil if you're at an optimum and use that to reduce your cost, but still get the same yield out of your crop? And so that's an area that we're working on and trying to make it more commercially viable from a financial perspective. Long term, I think there's just a lot of things that we'd like to look further at our product, because we think as we further develop these 11 patents and we really kind of push out from the original technology, I think there's so many things we can look at and go into. But I think it's the high P soils and the manure applications where we think we can add a lot of both environmental and yield positives. It's just trying to get more data to show that what we say it does, it does. And we've got good information at this point. Farmers are a tough group to get across the line with a new technology. So it's really trying to make sure they understand what's in it for them and what's important to them and how does our product get that to them. And so really a lot of the research goes back to, hey, I got to prove out, yes, it's efficacious and it does what I say it does. But then you've got to then look at the business side and say to a farmer, okay, what are the pain points for a farmer, whether it's application, whether it's cost, what is it, and how do we overcome those issues?
Yeah, and I'll say from our group, some of the things we're looking at, obviously we've had a great relationship with Phospholutions, having the opportunity to test some of their products out at Rock Springs and see the benefits and help understand how that technology can be positioned for our farmers. And that's been a really successful partnership there. Some of the other work that we've done is more sort of on the, I guess, environmental side. So a few years back, we published some work on manure injection and the reduced runoff that we get from using liquid injection toolbars, to get low disturbance injection and get that phosphorus off the soil surface. Another thing that I'll mention, this was actually an on-farm project, really led by the farmer, great guy down in Lebanon County, good cooperator with Del Voigt, our extension educator there. He was really interested in whether he should be doing deep placement of phosphorus, right? His soil phosphorus levels were kind of already optimum, but he was putting on these maintenance phosphorus applications, and he thought, putting it on the soil surface, I don't know if that's the best placement. I really want to get it deeper, maybe 6 to 8 inches deep, where that root system is growing. And so he actually used like a subsoiler with some fertilizer injection on the subsoiler, and actually came up with. I was really interesting to follow the yield results, and there was actually a negative yield hit or yield penalty associated with doing that subsoiling. So if his treatment structure, he had some subsoiling without any fertilizer added, he had subsoiling with fertilizer added, he had fertilizer added without the subsoiling, and kind of the way things were trending is that the subsoiling created about a 10 bushel yield hit from that soil disturbance. And I think it actually maybe created some sidewall compaction around the subsoiler. Adding the fertilizer with the subsoiler brought that yield back to kind of neutral. So there was a fertilizer impact. But then when he just dribbled that phosphorus on the soil surface in bands, that was the best return, right? He actually got a yield gain from just banding that phosphorus fertilizer on the soil surface as a liquid, as opposed to having the compaction from the subsoil. So I thought that was really interesting outcome, and it kind of shows the interaction of soil health and compaction issues, but still the nutrients. So I've sort of, I thought, well, that's an interesting idea. He's onto something with that placement, right? We talk about the 4 R's and the importance of placement, but it actually ended up with a negative return because of that. And, obviously the equipment costs and the fuel for all of that work too, versus just dribbling it on the soil surface.
Yeah, that's interesting. It's like you said, one of those 4 R's, we're changing one of them, but I mean, these processes are really dynamic, and there's compaction elements to it, soil biological elements to it that you're destroying or cultivating. That's really fascinating finding, and I'm interested to see where that goes. So, I will make sure that I put all of your guys' information in the show notes or whatever you guys want in order for people to get in contact or learn more about your lab or your company. And with that, Dwayne, do you have anything else?
No, I go back to something, we talk about 25, 30 years ago as soil being this black box that we don't know a whole lot about. And we're just, what's old is new again, right? We're still trying to figure out all these processes that happen within soil. And it is so dynamic and it's so interesting. We just can't stop learning about it. And we keep coming up with some new things. And some of this technology is just fascinating. And I can't wait to see where industry and the university, in partnership can go with some of this stuff.
Thank you guys for coming on today. We really do appreciate it. And to our listeners, we hope you enjoyed this as much as we did. And we'll see you on the next episode of the Agronomy Highlights podcast.